From the dawn of history through the end of the last century, agriculture was the economic and cultural anchor of the civilized world. During the last century, a major transformation has taken place. The Industrial Revolution swept rapidly through every developed country on the planet. Today, we are in the midst of another global transformation that is dramatically changing the way we live, learn, work, and play. It's called the Information Age, and it was launched in the middle of the 20th century by a single invention, the integrated circuit. Look around you. We live and work in a networked society. When you consider all of the products and services that are part of your daily life, you'll see they are things that would have been unimaginable a generation ago. The personal computer, cellular phones, fax machines, telephone answering machines, remote controls, electronic mail, the internet, video conferencing, automotive electronic systems. If you look closely, you'll see that the microchip is at the core of each of these products and services. The microchip has been the catalyst for the development of a global business community, has made possible medical breakthroughs of unprecedented proportions, and has created an environment for the rapid exchange of information and ideas that will shape the next millennium. In the 1950s, Texas Instruments invented the integrated circuit, a device now commonly referred to as the microchip. That first integrated circuit was a simple two-transistor circuit mounted on a rather large piece of germanium. Today, it's common to have many millions of transistors on a single silicon chip. The process of manufacturing microchips is complex, involving numerous painstaking procedures, many of which are performed at the submicron level. The best way to understand this fascinating process is to examine each step individually. From the transformation of raw metallurgical grade silicon into electronic grade silicon, to the making of silicon ingots, to the building of circuitry on a silicon wafer, to the packaging of the finished microchip. It all starts with sand, silicon dioxide, one of the most common minerals on Earth.
When silicon dioxide is heated together with wood and coke at over 3,000 degrees Fahrenheit, you get 98% pure metallurgical grade silicon, or MGS. With impurities of 2 parts per 100, MGS is pure enough to make aluminum products such as soda cans, but it's far short of the ultra-high purity needed to make a microchip. For that, MGS must be transformed into EGS, electronic-grade silicon, with impurities of only 1 part per billion. High-purity EGS is essential during all stages of microchip production and is a primary focus of quality control. Silicon purity is constantly monitored and tested throughout the manufacturing process. If impurities were evenly distributed throughout the silicon, identifying and measuring them would be relatively simple. But it is a law of physics that impurities tend to migrate to the boundaries of the material they inhabit. When the boundaries are semiconductor junctions, the smallest amount of impurity can cause an incorrect resistance value or an unwanted current leakage in the final microchip. Since the impurities tend to migrate to the junctions, impurity figures can be misleading. A material which has good purity characteristics at its center could fail quality control at its boundaries. To transform MGS into high purity EGS, the MGS is pulverized and made to react with anhydrous hydrogen chloride gas to form trichlorosilane. This process takes place in a fluidized bed at 300 degrees centigrade. Silicon tetrachloride and the chlorides of the impurities are formed by a method known as hydrogen reduction. Trichlorosilane is liquid at room temperature, as are the other chlorides of impurities which have been formed. Impurities are removed from trichlorosilane through fractional distillation, which is similar to the process used to separate high-octane gasoline from thicker hydrocarbons such as oil and kerosene. To make EGS from the trichlorosilane, a process called chemical vapor deposition is employed. A slim rod, which is a heated rod of silicon, is used as a nucleation point for the deposition of pure polysilicon, that is, pure silicon which does not have a regular crystalline structure. When a mixture of trichlorosilane gas and hydrogen gas flows over the slim rod, EGS builds up or grows over many hours until the desired thickness is obtained. The the pure electronic-grade polysilicon is removed from the slim rod and crushed into egg-sized chunks. In this form, the EGS is shipped to microchip manufacturers, where it will be transformed once again.
The raw EGS, or polysilicon, which arrives at the manufacturer, does not yet have the crystalline or lattice structure that it will ultimately require. When struck with a hammer, a polycrystalline material, such as polysilicon, will shatter like glass into many pieces. On the other hand, pure crystalline silicon, like any crystalline material that has a lattice structure, will fracture on a cleavage plane. When a single crystalline structure is struck with a hammer, it will break in geometric pieces. During the next step in the manufacturing process, the raw polysilicon will acquire a lattice structure. We call this step growing a silicon ingot.
Microchips are manufactured on silicon wafers, which are sliced from a single silicon ingot. A typical ingot is 8 to 12 inches in diameter and about 2 to 3 feet long. To grow silicon ingots, the raw polysilicon is delivered to a facility with vertical ovens. The polysilicon charge is placed in a quartz crucible or furnace liner, which is washed with deionized water and then vacuum dried to remove any contamination that might have resulted from shipping and handling. The crucible will hold not only the chunks of polysilicon charge, but also dopant impurities. These dopants will determine the electronic properties of the crystal ingot that will be produced. A furnace charge or load is prepared according to the specifications of the requesting wafer fab. Since the wafers on which the microchips will be manufactured are cut from the silicon ingot, specific crystalline orientations as well as electrical characteristics are defined at this stage. A computer database provides details of the ingot specifications, including wafer resistance, type of semiconductor, wafer diameter, thickness, length, and other pertinent information. This information is used to prepare the proper ratio of polysilicon and dopant impurities. All details concerning each charge are recorded on a computer printout, referred to as a traveler. The charge is made from chunks of raw polysilicon, a measured amount of dopant, such as pure boron or phosphorus alloy, a seed of crystalline silicon to determine the crystal structure of the finished ingot, and this is used to start the crystal growth at a particular orientation, and a clean, dry crucible. The size of the load and crucible depends upon the size of the crystal ingot to be grown. After preparation, the charge is taken to the crystal growing furnace. Most manufacturers use vertical furnaces that work on the CZ or Czochralski crystal growing method, commonly called crystal drawing. This crystal drawing takes place in an electric furnace which will reach temperatures greater than 2,500 degrees Fahrenheit. The quartz crucible that holds the ingot ingredients must withstand the tremendous heat of the melted silicon. The quartz liner holding the charged mixture is placed in a carbon bowl or susceptor, which is then placed in the furnace tank. A small piece of seed silicon is attached to a motor-driven molybdenum chuck, which is suspended on a stainless steel wire from a motor platform at the top of the furnace. Once the charge has been placed in the furnace tank, the furnace is closed. Then argon, an inert gas, is pumped into the furnace. This forces all of the air out and prevents the molten silicon from reacting with any contaminants. A typical crystal furnace requires about 150 kilowatts of power, enough to power 10 homes, and a continuous flow of recycled cooling water. Computer-controlled motors rotate the seed crystal that is suspended from the top of the furnace in a counterclockwise direction, while rotating the crucible clockwise. This rotation begins the drawing process. When the polysilicon mixture melts to the consistency of water, the seed crystal is lowered slowly into the molten silicon, just past the point of contact. It is then slowly pulled upward as the seed and molten silicon are rotated in opposite directions. To draw the silicon crystal from the crucible, the mixture must be kept very near the freezing temperature of molten silicon, or about 1410 degrees centigrade. The speed of the drawing mechanism varies, depending on the diameter of the finished ingot required. An 8-inch diameter crystal ingot may require a vertical pulling speed of 2 inches per hour, while a thinner ingot will require a faster rate. Most crystal furnaces are controlled by computer. Some have a camera which monitors the molten ingot through a viewing window, while others employ a scanning photodetector. These devices provide precise ingot diameter data to the furnace computers that in turn control the motor speed, temperatures, and drawing rate. The more uniform the ingot, the less waste there will be during trimming operations.
After the crystal ingot reaches its desired length, preparation is made for it to be sliced into thin wafers. The precise thickness, diameter, and crystal orientation of the wafers are critical in the manufacturing of microchips. As you'll see, the process is automated to achieve maximum precision.
Once the crystal ingot reaches its maximum desired length, it is removed from the furnace with an automated lifting arm. The furnace is then cooled, inspected, and prepared for the next charge. Meanwhile, the cooled silicon ingot is taken to an area equipped with lathes, saws, and grinders, where it is processed into wafers. First, the tapered ends of the ingot are removed. It is then placed on a lathe and ground until the ingot is perfectly round. Precise diameter of the ingot is checked with micrometer calipers. The orientation of the crystal planes is very important for the many subsequent manufacturing steps. To check crystal alignment, the ingot is placed in an X-ray diffraction device that produces readings that determine its crystal orientation. Once orientation is determined, a flat surface is ground along the length of the ingot. This flat area provides a key to the crystal characteristics for processes further down the line. It also permits easier alignment for handling during wafer fabrication. Next, the ingot is placed in a diamond saw and a few wafers are cut for measurement and testing. All wafers undergo stringent testing throughout the manufacturing process. Factors such as thickness, diameter, flatness, and uniform resistance are constantly checked against specifications. Tests for characteristics such as resistance are performed using a non-contact resistivity probe. To keep the thin wafers securely in place as they are sawed from the ingot, a carrier block is glued to the flat side. Then the ingot is placed in a very fine-edged diamond drum saw and sliced into wafers 20 to 30 thousandths of an inch thick using precise automation. The wafers are washed in a bath of deionized water to remove all particulate matter, then placed in a grinder to form a smooth profile on the razor-sharp silicon edges. The next step in the process is called lapping, during which the wafers are loaded onto a machine which spins them in an orbital motion. This lapping takes place on a table which is rotated between two surfaces as the wafers are lubricated with an aluminum slurry. The finished wafers must have a surface flatness of plus or minus 3 microns. After the lapping process, the wafers are chemically etched using potassium hydroxide to remove damaged layers of silicon. This step is critical because without this stress relief etching, the wafers would warp. Finally, the new cut wafers are polished with a weak caustic solution of fine abrasive slurry. After final inspection, the wafers are shipped to wafer fabrication facilities for further processing.
Now we have a thin blank silicon wafer grown from a single silicon crystal. It's difficult to imagine how this wafer will go on to become digital signal processors, memory chips, or microprocessors that will be at the core of our personal computer, fax machine, automobile, or video camera. But it does. And the next very complex phase of microchip manufacturing, referred to as fabrication, takes place at a facility called a wafer fab.
The individual features of a microchip are many hundreds of times smaller than the width of a human hair. As circuit geometries continue to get smaller, airborne particulate contaminants become a major quality control concern. A single impurity, detectable only with a high-power electron microscope, can cause catastrophic microchip failure. Because of the concern for purity in microchip manufacturing, the wafers are processed in clean rooms. For each cubic foot of highly filtered air inside a clean room, there is less than one particle greater in size than 1 micron. This is 10,000 times cleaner than the air inside a typical hospital operating room. Clean, filtered air is passed through the wafer processing area from ceiling to floor at about 90 feet per minute, which means the total air volume in the room is changed often. Persons entering the building in which the wafer fab is housed are required to wear special shoes or cloth booties over their street shoes to keep trapped-in dirt out of the building. Before anybody can enter a clean room, they must dress in special lint-free clothing and pass through an air shower. The clothing includes a lint-free jumpsuit, mask, head cover, gloves, eye protection, and special shoes. The air shower is similar to a vestibule-type airlock. Upon entering the vestibule and closing the door, air is forced out of nozzles mounted on the wall to dislodge any remaining particles that might still be clinging to clean room clothing. Before a person enters a clean room, each and every piece of clean room clothing must be changed and gloved hands must be washed with deionized water. New wafers from the crystal growing facility are delivered to the clean room in vacuum-sealed containers. Obviously, it is important to handle wafers very carefully during the entire fabrication process. Wafers are transferred between carriers or boats using automatic wafer transfer stations to prevent microscopic dust from being generated as the wafers roll from one container to the next. Throughout the process, wafers are handled using a unique wafer backside vacuum tool to eliminate any possible contamination from handling, even from gloved hands. Incoming wafers are inspected, cleaned, and rinsed. They are then placed in clean containers along with a bar-coded information card which provides specific, detailed information and a history of the wafer.
The many fabrication steps the wafers undergo are complex and will depend on the type of device being made on the wafer surface. Basically, there are 7 main steps to processing a microchip from a wafer. They include deposition or growing film, diffusion, patterning with photolithography, metallization, ion implantation, etching, and testing. Each of these steps may be repeated many times and in any order during the fabrication process.
Deposition or growing film is always the first step in the fabrication process. Its purpose is to install an electronic surface on the wafer's crystalline silicon substrate. Wafers must be cleaner than deionized water can make them, and to accomplish this, the wafers are bathed in solutions of chemicals such as hydrochloric acid, hydrogen peroxide, hydrofluoric acid, and sulfuric acid. These strong, corrosive liquids remove mineral and organic contaminants from the surface of the wafer. Silicon dioxide layers are deposited on the wafers as a protective coating during fabrication or as a mask for high-temperature deposition or implantation. By adding phosphorus to the silicon dioxide, the deposited layer also acts as a sodium barrier. The 2 most important control factors in deposition and growing are layered thickness and resistivity. These and many other wafer parameters are constantly checked throughout the wafer fabrication process to guarantee high-quality, high-yield processing. Another type of deposition process is metallization. Metal is used for the many interconnects on a microchip as well as the bond pads through which the chips will be connected to the outside world. In metallization, an insulating layer is first deposited over the entire wafer where metal is to be deposited. Then, the metal is sputtered over the insulating layer. During sputtering, the method commonly used to deposit metal on a wafer, the wafers are mounted in a chamber which includes a target, a plasma source, and an argon gas source. The target is held at a negative potential, while the argon ions are positively charged. The positive ions are accelerated toward the negative target. The argon atoms hit the target at a high rate of speed, breaking off some of the target. The minute, broken-off pieces land on everything in the chamber, including the wafer. Metals like aluminum, molybdenum, platinum, gold, titanium, and tungsten, and alloys like doped polysilicon are commonly used for the chip interconnects and bond pads. The diffusion process takes place in a quartz-lined furnace similar to an oxidation furnace. Dopant gas, which changes wafer characteristics, is forced to flow over the wafers. During this process, atoms of the desired impurities settle on the wafers. When the dopant gas is turned off, the impurities are given time to diffuse into the wafers. Finally, the wafers are heated for a short time to anneal the surface back to a monocrystalline state. P-type dopants may be diffused into wafer surfaces using boron, and N-type surfaces are formed using phosphorus or arsenic. As in other steps, these elements are available in carrier alloys. Quality control is performed after each processing step. One such quality control test for surface faults involves reflecting a light beam off the surface of the wafer and analyzing the reflected light. Diffusion can be accomplished using solid or gaseous dopants at various temperatures and pressures. For example, when diffusion is called for late in the fabrication process, low temperatures are used so that the existing metallic structures are not destroyed. There's another way to introduce dopants into a wafer. It's a process called ion implantation. This process uses a carefully controlled ion beam from a linear accelerator called an ion implanter to bombard the wafer target. The emitted ions travel through a magnetic field which bends the electron beam. Depending on the charge of the particles passing through the magnetic field, different species of ions will be separated from the beam by changing the angle of the exit trajectory. The desired ions are focused by the beam scanner and onto the wafer. The accelerated ion beam is electronically scanned over the surface of the wafer. The more ions in the beam, the higher the beam current and the more dopants the beam will deposit in a given time. The higher the beam voltage, the deeper the ions will be implanted in the wafer. The next major step in processing is patterning. A patterning process called photolithography employs a series of reticles and a photosensitive material called photoresist. First, reticles are made which determine all the areas of a particular microchip layer to be patterned. The unmasked or exposed areas of the wafer will be diffused or layered with dopants. Reticles are generated using data which is supplied by the circuit designer. Depending on its complexity, the wafer may require from 10 to 20 or more reticle steps to pattern everything from insulated silicon islands to metal interconnects. Photolithography reticles are very similar to photographic reticles inasmuch as they allow light to pass only through those areas from which the reticle material has been removed. They are made by etching a thin metal sheet or metal-coated glass using an electron beam. This beam operates like the beam in a television tube. It moves back and forth, scanning a pattern on the blank reticle. To prepare a wafer for photolithography, its surface is coated with a uniform layer of resist, so called because it resists the plasma etching. When light is used to expose the resist, it is called photoresist. Photoresist is spun onto a wafer at high speed to form a uniform layer. Photoresist material, which is carbon-based, is particularly hardy when used with gas plasma during the dry etching process. Once the wafer has been coated with photoresist and the resist has been baked to harden, it is exposed to ultraviolet light through the photoreticle. Because of the extreme detail required, the reticle is usually made to expose only small areas of the wafer surface, one area at a time. To cover the entire usable surface of the wafer, the reticle is stepped over the wafer using precise computer positioning controlled by a device called a stepper. The wafers are aligned by a computer which scans special patterns which have been printed on the reticle and etched on the wafer. This step method of exposure is capable of geometries as small as 0.12 microns. After exposure to the light, the wafers are immersed in a developer to remove that portion of the photo etch which has been exposed. An acid bath with a fully automatic robotic arm receives the wafers in one end and performs all the dipping and rinsing operations behind a protective glass called a hood. Once the wafers are developed, they are rinsed and prepared for the next process. The wafer is checked to make certain that all surfaces, edges, and depositions defined by the reticle step are correct. Another major step in the fabrication process is etching. During this step, a pattern is etched onto a wafer using an electronic plasma process called dry etching. Once the desired areas under the photoresist have been developed and cleaned, they are loaded into a plasma etcher. A plasma is formed when molecules of gas are excited enough to react with that part of the wafer's surface not covered with resist. The hot plasma takes the place of the corrosive chemicals used in wet etching. The gas is excited or ionized using a high-frequency field in a chamber called a reactor, from which all the air has been evacuated. Plasma etching is a low-temperature process which takes place below 450 degrees centigrade. The type of gas used in the plasma reactor chamber determines the type of layer to be etched. Normally, the basic etchant will be chlorine, fluorine, or oxygen, which is carried in gases which react readily with the exposed surface. Timing of the etching process is very important. Under-etching causes incomplete patterning. Over-etching can cause undercutting of the masked areas, which may render the entire wafer useless. The advantage of dry or plasma etching is higher resolution and better control of element dimensions. The wafers are then treated with a protective overcoat of silicon nitride. The nitride is deposited over the entire surface except for the bond pads on the chips. The bond pads, which are the points of connection to the pins of the microchip package, are also used for testing. That brings us to the final processing step, multi-probe testing. The wafer is placed on a computer-driven frame which positions every bond pad directly under a probe card. The probe card has numerous tiny finger contacts that are stepped to touch the metal bond pads on every device. This multi-probe unit steps along, checking each chip on the wafer, row by row. These checks include a continuity or go-no-go test, as well as functional and parametric testing.
There is one more wafer fabrication process we should review. It's called characterization, and it serves all areas of silicon preparation, chip fabrication, and packaging. A characterization lab is responsible for analyzing and assuring the materials which comprise a microchip. These materials include silicon, bond pads, insulators, dopants, metals, and chemicals used in wafer processing, lead, and packaging. Let's take a look at characterization.
It is imperative that a characterization lab have the most current measurement and analysis equipment. This equipment must be capable of examining single atoms, detecting minute amounts of impurities and substances, and accurately scanning for lamination or bonding problems. The lab may be utilized at any step during the entire manufacturing process. The lab's services require not only very sophisticated equipment, but also a highly skilled team of physicists, chemists, materials scientists, and technicians. One piece of equipment is the acoustic microscope, which is used for examining microchips for packaging problems, such as the delamination of the plastic encapsulation of the case. This instrument uses a transducer which focuses, transmits, and receives 25 to 75 megahertz sound waves. Other tools, such as the scanning tunneling microscope and the atomic force microscope, enable researchers to study surfaces at a microscopic level with unparalleled resolution. A fine needle tip rides at a microscopic distance above the surface of the sample and maps topology as it scans back and forth. It displays a three-dimensional color image. These electronic microscopes can detect positions of individual atoms on a surface with a resolution of less than 1 angstrom. Some of the other techniques used in the characterization process include Rutherford backscattering spectroscopy, linear acceleration, molecular beam epitaxy, scanning electron microscopy, and polymer chemistry analysis.
In the final major manufacturing step, the wafers are sliced into individual microchips and packaged, complete with the cases and leads, ready for use by the customer. This process is highly automated. It begins when the wafers are received from the wafer fab facility.
First, the wafers are sliced into separate microchips. This is done with a very fine, sharp, diamond-tipped saw. A robotic system picks up the tiny chips and mounts them on lead frames using an epoxy or polyamide adhesive. The type of lead frame will differ depending on the type and size of the chip and pin configuration. The chips are then bonded to the lead frame connectors. Tiny gold wires connect each bonding pad on the chip to each pin on the lead frame. The bonding process is monitored and inspected by a video recognition system run with artificial intelligence software. A camera checks for the proper number of bond wires, possible shorts, and alignment. Once the chips and lead frames pass inspection, they are placed in a mold that forms the final package. Plastic epoxy or ceramic material is usually used for encapsulating the chip. While the microchip lead frames are still together, the packages are printed with part number, logo, and lot number, a process called symbolization. The microchips are then cut apart by a large press, which bends the leads at the same time. The packages are electrically, electronically, and mechanically inspected, and each part is screened for defects, such as cracks in the plastic, uneven plating, or poor trimming. After inventory, the parts are checked for compliance with all electrical specifications, both AC and DC. The devices then undergo a lot acceptance to ensure that the devices meet strict industry statistical quality control standards before finally being shipped to the customer.
The process of manufacturing a microchip is so complex and intricate, it's hard to believe it was ever developed, let alone fine-tuned for mass manufacturing like it is today. And engineers and scientists continue to make brilliant improvements to this fascinating process. This tiny device has become so important to our daily lives, it's difficult to imagine life without it. One thing is certain, tomorrow's world will be shaped by smaller, faster, and more powerful microchips, devices that will continue to alter the way we live, learn, work, and play.